This is the last part of section 2.5 on graphing these higher order polynomials. And when we left off last time, we kind of looked at all of the effects that can happen to a graph. So we're going to start by summarizing them a bit here on page 112. So here's my summary for a polynomial of degree n. So the highest power here is n. First of all, if x minus r is one of the factors of the polynomial, then we know that x minus r has to equal 0 to get a 0 of the polynomial, which when I solve that would just give me x equal r. So x equals r is a 0 of that polynomial. And if I wanted to formally write it as an x-intercept, that would be r comma 0. So the factors and the zeros very closely, the factors, the zeros, and the x-intercepts, all very closely related. All right, the next summary is about multiplicity. If my factor x minus r is being raised to some power m, then actually that x equals r occurs m times. So we say, yes, x equals r is still a 0, but it's a 0 of multiplicity m. I was often abbreviating that as capital M of whatever the degree was. Capital M of little m, I guess, in my notation right here. And then we noticed that if m was an odd power, so we had odd multiplicity, the graph would cut through the x-axis. And if m was even, the graph would bounce off the x-axis. All right, zeros versus x-intercepts. If my polynomial has degree n, then there must be n zeros, as long as I count multiplicity. However, only the real valued ones are actually x-intercepts. So that means the total number of x-intercepts is less than or equal to n. If these are all real, unique zeros, then we will have n x-intercepts. But if there's some repetitive zeros, or if there's some imaginary zeros, they will not lead to more x-intercepts. So the fact that it's less than or equal to n is due to things like multiplicity or imaginary zeros. Things that cut the total number of x-intercepts down. All right, as far as the number of turning points, to be honest, I guess I kind of stopped keeping track so much of that, but it looked like we kind of lost the pattern there. The very, very first problems we did in part A, the first video, we always had n minus 1, one less than the degree. Later on, sometimes there were even fewer than that. So I'm just going to say the number of turning points is less than or equal to n minus 1. So if I have a fourth degree polynomial, there would be 3 or fewer turning points. And then finally, last couple things here, my end behavior. The end behavior depends on the degree, right? So the end behavior of my graph was the same as the end behavior of y equals x to the n. Right? If n is odd, the end behavior was down to the left and up to the right. And if n is even, that's the parabola-like ones, then the end behavior is up in both directions. All right, lastly, something I haven't been talking about a lot, but I just want to remind you from things we've done in the past. The y-intercept of the graph can always be found by just setting x equal to 0. So it's the y when x is 0. We're actually going to use that in the next couple examples, so it was a good time to review it. All right, so there is our summary page, and that's actually a good one to sort of keep handy as you're doing these problems, because if you forget something, it's probably somewhere on this summary page. All right, the next two examples are going to take what we've been learning and reverse the way the information is given. Up until now, I've given you a formula, a function, and asked you what the graph looks like. In the examples on page 113, it's exactly the opposite. I'm going to give you a graph and say, could you tell me what the function is? Well, let's see. I've got a graph here, and so much depends on the x-intercepts, or zeros. Let's start with those. See 3 of them. So since those are the x-intercepts, I know the zeros of my function must be x equals -4, x equals -2, and x equals +1. The graph definitely cuts through the x-axis at all of those points, so I would anticipate, that those would all have multiplicity 1. Right, the smallest possible multiplicity for cutting through, and I don't see that little wave that might indicate it's something bigger, so we'll stick with 1. All right, that means that this function could be y equals, and I'm going to leave myself a little space here, and then I'm going to start writing down factors. If -4 is a 0, x plus 4 must have been a factor, right? That way when I set this equal to 0, I get x equals -4. Same thought process here. -2 is a 0, so x plus 2 is a factor. And here, x minus 1 would have to be a factor. When I set it equal to 0, then I get x equals +1. Since those were all multiplicity 1, I'm just going to have first powers on all of those terms. And then the only thing I may not have yet taken into account is there could be a GCF. So I'm going to abbreviate that with just the variable g in front of there, and I have to worry about that g in just a minute. Okay? So that gets me really about 90% of my function. The zeros are the leads to the factors, and it gives me most of my information. All right, how am I going to go about getting that g? This is where the y-intercept can really help me. On this graph, my y-intercept's right here, 5, 6, 7, 8. So that's the point 0, 8. I'm just going to go ahead and plug x equals 0 and y equals 8 into this equation, and that should allow me to solve for the g. So let's do that. Y is 8 equals g times, and I'm putting 0 in for the x every time. So let's see, 4 times 2 is 8 times -1. That's -8, so I have g times -8. And if I divide both sides by -8, g is -1. So my final answer for this polynomial function is going to be -1 for g times the x plus 4 times x plus 2 times x minus 1. And I'm not requiring you to multiply these out here or in the homework. You're fine to just leave it like that in its factored form. Okay. All right, so that's the process. I do want to mention one thing. The fact that g turned out negative is actually not at all surprising to me, because look at the end behavior. This is going to be a cubic function. X times x times x would be x to the third. And normally, end behavior for a cubic function is up on the right and down on the left. So I knew this had been reflected. I knew this had been flipped because of the up on the left and down on the right. Exactly opposite of what I would have normally expected. Now, I didn't necessarily know it was -1. Could have been negative something else, so we still needed to go through that process, but just wanted to point that out. All right, let's try one more problem like this. I'm starting by identifying my zeros. Here, here, and here. So -1, 2, and 3 are my zeros. And I want to be really careful with this one, because notice this 0 right here at -1, the graph just bounces off. It doesn't cut through the x-axis at that point. That -1 has to have an even multiplicity. Multiplicity of 2 or 4 or 6 or something like that. Because the original directions said smallest possible degree, I'm going to use the smallest possible even number and say I think that has multiplicity 2. These two the graph cuts through. So those would be odd multiplicities. Smallest odd number is 1. And I don't see that wave shape telling me that it's anything higher, so I'm pretty comfortable with that. All right, so again, there may be a GCF that I don't know yet. I'll have to come back and figure that out later. But from these zeros, I know the factors would be x plus 1. And with a multiplicity of 2, that occurs twice, so I'm going to square that. Next, I would have an x minus 2, and then an x minus 3. Those are both multiplicity 1, so just powers of 1 on those. All right. I'm going to find the g, and I'm going to use the y-intercept again, but I just want to make one remark. This goes up on the left and up on the right. And notice I have x squared times x times x. This is going to be 4th degree. So up on both the left and right is what I would expect. I think I'm going to get positive g this time. Let's check it out. Here's my y-intercept. I think I'm counting by 2s. 2, 4, 6, 8, 10, 12, yeah. So my y-intercept is 0, 12. And I'm going to plug that in for the x and the y values. Y is 12 when x is 0. So let's see, 12 would be g times 1 times -2 times -3 would be 6. And so if I divide both sides by 6, I can see that g is 2. So my common factor did have a vertical stretch of 2 on this one. And I can say my final answer then is going to be y equals 2 times all of that. We will not be able to predict formulas if we have an irreducible quadratic. That's beyond the scope of what we can do here. But if we have linear factors, even if they're repeated linear factors, we can usually predict the equation based on the graph. I'll make one more remark. If I wanted to, I could, of course, check this pretty easily. If I just typed this equation into Desmos, I could compare it and make sure that I get that graph. So let's take a minute and I won't do the first one. I'll just do the second one. And there we go. It certainly looks a whole lot like what we just saw. Compare it to what you see in print. There's that y-intercept of 12. Right? There's the bounce off at -1 and the cut through x-intercepts at 2 and 3. It's exactly what we expected to see. So, looking good. All right, there's one other type of problem on your homework, and honestly, this isn't really anything all that new compared to what we've already been doing, but I'm just going to run through a problem or two here so that you know exactly what I'm expecting when you see these formats for problems in the worksheets. All right, so I've given you a polynomial. In this particular case, it happens to already be factored. And we're being asked to do all of these things, analyzing, and I probably should be specific, analyze by hand, and then draw a reasonable graph. Of course, if there's things that I can't graph by hand, I do have a Desmos or a calculator to help me if I need it. All right, let's start with the degree. This would be an x squared. This factor is an x to the first. This factor is an x to the first. So 2, 3, 4. This is a degree 4 polynomial. Actually, I think I meant to put that over here. The zeros with their multiplicity. I would have an x equal 1 when I set that equal to 0, right? X would be 1. And that's got a multiplicity of 2. Setting this factor equal to 0 would give me x equal -4. That's going to have a multiplicity of 1. And this last one, x equals -2, also with a multiplicity of 1. All right, the x-intercepts and the behavior at the x-axis. So my first x-intercept here would be 1, 0. And because it's an even multiplicity, this is going to bounce off the x-axis. My next x-intercept would be -4, 0. Odd multiplicity, so this one cuts through. And then my last 0 here is the -2, so as an x-intercept, that would be -2, 0. And once again, odd multiplicity means that it cuts through. All right, next, the maximum number of turning points, right? The degree is n, and the maximum number of turning points is always 1 less than the degree. So in this case, 3. When we actually look at it, there may not be 3 turning points. We'll see. But there can't be any more than 3, right? That's the most I could have. All right, looks like my hole punch got the best of me, but that should have said y-intercept there. So for the y-intercept, we put in x equals 0. So y will be 0 minus 1 squared times 0 plus 4 times 0 plus 2. Let's see, when I square, that'll be positive, so 1 times 4 times 2. My y-intercept on this one's going to be 8, so 0, 8. And then the final thing I'm being asked to do is to determine the end behavior. This is degree 4. So this is going to be like y equals x to the fourth. Even power, so parabola-like, both ends go up. So my end behavior is going to be up to both the left and right. Okay. So that's the kind of analysis that I'm looking for in the chart that I'll be giving you on the homework. And then putting all this information together, let's see what we can draw. Let's see, starting with my zeros, 1, -2, and -4 are the zeros. Might as well put the y-intercept in there as well. 1, 2, 3, 4, 5, 6, 7, 8. Those are the 4 specific points that I know. And then I'm going to start up to the left. So I'm going to start up here. I'm going to come down and I'm going to cut through at the -4, 0. Come back up. I'm going to cut through again at the -2. And then I got to go way up here to the y-intercept, quickly come back down, and bounce off at the 1, 0. That's about the best that I can do by hand. Now, it may be that this goes down much further. It may be that this goes up much further. I can't really tell by hand, so that would be the best I could do that way. But I should have the basic shape of the graph correct. Of course, if I wanted more accuracy, I could always go over and check it out on Desmos. Oops. There we go. And yeah, again, notice it's the same basic shape as I drew. It looks like it did go down a bit further than what I had, guessed in my guess, and it actually went up a bit further above the y-intercept. But I certainly had the cut-throughs at -4 and 2, and the bounce off at 1 correct. I had my end behavior correct, and I had the basic shape right. Again, without calculus, knowing exactly where that maximum and minimum are is not possible. So that's something, if you take more math, which I hope you will, you'll find out how to do that in a later class. All right. I believe I have one more example, so let's finish off with this one. All right, this one, notice it's not in descending order. I could rewrite it in descending order if I wanted to. -x to the 5th plus 3x to the 4th, just to emphasize that the degree really is 5. So usually we call our degree n. And to get the zeros this time, it's not quite as straightforward as last time because I don't have the factored form yet. But the factored form, fortunately, isn't too tough to figure out. Let's factor that right up here. I have a GCF of x to the 4th. And when I factor that out, I'll get a minus x and then a plus 3. So, x to the 4th equals 0, which is going to give me x equals 0, but with multiplicity 4. Or minus x plus 3 equals 0, which is going to give me 3 equals x, and that just has multiplicity 1. All right, let me turn that into x-intercepts. This x-intercept, 0, 0, has an even multiplicity So this is going to be a bounce off. And this multiplicity, or excuse me, this 0 would translate to the X-intercept 3, 0. And it only has a multiplicity of 1, odd multiplicity, so this is going to be a cut through. Maximum number of turning points, 1 less than the degree. So this is degree 5, meaning the most turning points I could have would be 4. Might be less than that. The Y-intercept, I put in x equals 0. And so y would be 3 times 0 to the 4th. Minus 0 fifth, which is still 0. So the origin 0, 0 is my y-intercept. And in terms of my end behavior, the degree is 5, but notice that there's a negative multiplier in the front here. So I'm actually going to have an odd degree. It's going to be like x to the 5th, but reflected across the x-axis. So really like y equals minus x to the 5th. Normally our odd powers are the waves that are up to the right and down to the left. Because of that negative, I'll reflect that, meaning it would be up to the left and down to the right. All right, let's see how much I can graph based on that information. I'm going to start by putting in my x-intercepts, 0, 0, and 3, 0. And since the y-intercept was also 0, 0, I actually don't get any extra information there, so not a ton here. But let's see what we can do. We know we were supposed to start out up to the left, so I'm going to start out up on this left-hand side. And then when I get down to the 0, that's a bounce off. So come down here, bounce off. I'll have to go up and come back down to the next 0, and 3, 0 is a cut through. And that's really all she wrote. Right? Notice up to the left, down to the right, exactly the end behavior that we predicted. So I'm actually pretty comfortable with that graph. I'm going to guess that I have the basic shape correct. Again, that maximum right there might be way taller than what I have. I just don't know, but since I didn't put a scale on my y-axis, I can get away with it. Let's check. I always do that. All right, my function was 3x to the 4th minus x to the 5th. And there we go. Notice with that high power, that x to the 4th power, my graph was a bit flatter near the origin, but it was a bounce off. So I got that right. Probably just could have flattened it out a little bit. There's the maximum that we predicted, and there's the cut through at 3, 0. So my basic shape was pretty good, just maybe could have flattened it out a little bit more near the origin. All right, those are the kinds of problems that you'll be doing for homework, the ones that we've actually done in this video. And so I'll have you take a look at that, and we'll be back next time for 3.6.